네. Yeah. So today, so last time we discussed the so-called ratio test. So what was the ratio test? Ratio test was basically comparing your series with the geometric series, right? And the nested interval theorem, well, is this. So in order to discuss the nested interval theorem, then first I will need to explain the meaning of the nested intervals. So first, we have a sequence of interclosed intervals. So that is, we know the sequence of numbers, right? But what is the sequence of intervals? So, well, just a sequence, bunch of sequences. But this time we are discussing the sequence of closed interval, and we say these intervals are nested. Okay, so first, so do you know the meaning of the closed interval? Yeah. Closed interval is, well, usually typically means the interval that contains both endpoints, right? Both endpoints. So that is the closed interval. So all these guys from I1, I2, I3, In, they are all closed intervals, and they are nested. So that means In contains In plus 1. So this is something like this. So I1 is the largest one, and since I2 is contained in I1, so I2 must be slightly smaller than I1, and I3 is even smaller than I2, and so on, right? So it keeps getting decreasing, shrinking and shrinking. So these sequence of intervals, we say they are nested closed intervals. Okay. Okay. All right. And it says then the intervals In have at least one point in common. So in other words, if I1, I2, so in other words, if they are closed and nested intervals, then we want to consider these infinite intersections of these intervals. I1 intersection I2 intersection, I always feel like the limit of this sequence of intervals. So we have not discussed the definition of the limit of intervals. So for now, please allow me to write down like this. Okay, let us consider this infinite intersections of these intervals. And it says if INs are closed and nested intervals, then at least one point in common. That means this infinite intersection is a non-empty set. So this is the claim of this theorem, right? Just one more. And if the length of the intervals tends to 0, then there is exactly one point in common. So what does it mean? So if the length of interval is tending to 0, then there should be precisely one guy in this infinite intersection. Okay. Okay. All right. Well, this sounds very obvious. Anyway, so I will provide you the proof. Since all these intervals, they are closed intervals, so I write down these endpoints of In to be An and Bn. and they are nested. Okay, since they are nested, so AN is this endpoint and BN is that endpoint, right? Yeah. And since they are nested and nested, therefore, this endpoint must be increasing, right? And the other endpoint should be decreasing. So we can find an increasing sequence, AN, and the another guy, BN, is decreasing sequence. And obviously, AN must be less than equals to BN. Okay. Okay. I want to focus on the sequence AN. AN is increasing, right? But anyhow, AN cannot increase forever. Increase to positive infinity because, well, AN, even though AN is increasing, but AN cannot exceed B1, say B1, right? I mean, precisely speaking, AN cannot exceed any of B's. But, well, the point is, AN is increasing and bounded above. Likewise, Bn is, since Bn is decreasing, although Bn is decreasing, but Bn cannot exceed, say, A1. Right? So Bn is decreasing and bounded sequence. So those two guys are there, or both increasing bounded above or decreasing and bounded below. So therefore, because of the monotone convergence theorem, you have two real numbers such that and okay. So these two guys are converging sequences. And I want to claim that A is less than or equals to B, which is pretty obvious. But anyway, at least once in your lifetime, yeah, you need to see the proof of this. Why? Suppose not. I'll try to prove by contradiction. If A is greater than B, then there must be some contradiction. Then we define our epsilon to be A minus B over 2. And this is, which is clearly a positive number, right? Anyway, for this epsilon, I can find two integers n1 and n2 such that if n is greater than n1, then A minus B over 2, an A plus A minus B over 2. And if n is greater than n2, then the same thing. Because these sequences are converging to A and B's respectively, so we have these four inequalities if this index is greater than this number. Okay, all right. And hold on. Yeah, so before I move on, so I would like to simplify these two things. Simplifying this guy is going to be A plus B over 2. All right. Oh yeah, good. And this is also a plus b, everything divided by 2. Yeah. Turns out to be they are the same numbers. All right. Now I can derive a contradiction. Now for index that is greater than n1 and n2. 네.
번지식의 a 더하기 2분의 1-b가 a 더하기 2분의 1-b.
잠깐.
번지는 거.
요거요? 잠깐만, 제가 틀렸나? 아. 그쵸. 이거는 a고 죄송합니다. 감사합니다. 네. Thank you. Yeah. But I have an excuse. I have really stuff. I'm not feeling very good. 죄송합니다. Okay, thank you. So for if your index is greater than both of these two integers, then what kind of contradiction do I have? Then, well, in this case, we have these 4 inequalities at the same time, but I will just use these two. Bn is less than a plus b over 2, and which is less than an, right? And this is a clear violation of this inequality, right? An always must be less than or equals to Bn for all n's, but this is not. So this is a contradiction. Okay. Okay, so so an must be less than or equals to a because, an is increasing sequence. Therefore, its limit must be the upper bound of this the sequences. And also we know that this is less than b because of this claim. And also this is less than bn. So we have these inequalities. Okay, so we are done. Almost done. So for if b was strictly less than a, then this guy will be an empty set. Therefore, it cannot contain anything. But however, since we have these inequalities, so this guy is clearly a non-empty set. Therefore, I can find some number from this interval. Then this x must be in an and bn, which is I for all n, right? This means this x must be the member of this infinite intersection. Good. Okay. What's next? Okay. Oh, also, suppose the length of the interval is tending to 0. In this case, length of interval tending to 0, that means a and b, they must be the same number, right? So if a is b, then this infinite intersection only contains just a single number. Okay. So this ends the proof, the nested intervals. All right. I want to emphasize this. So Okay, just let me go back to the statement. And well, at the very beginning, we are assuming that each of these sequences must be closed intervals. So that means if your intervals are not closed, then in that case, even if your intervals are nested, but this infinite intersection could be an empty set. Can I find such an example? Yeah, we have this. If IN is not closed, then this infinite intersection may be an empty set. For instance, suppose that this is my interval. This is an open interval. It does not contain two endpoints, right? 0 and 1 over n. Why well, is it nested? Yeah, because as well, as n increases, the interval is getting smaller and smaller. Therefore, yeah, I am sure that these intervals are nested. But, well, the infinite intersections of this interval is an empty set, right? Yeah. Why? Because suppose that these guy were not an empty set. And well, but however, even in that case, this infinite intersection only can contain a strictly positive number, right? Suppose that, therefore, let us say that this guy has some positive real number, say epsilon. But in that case, well, if a epsilon is in this infinite intersection, then, but no matter how small your epsilon is, you can still find an integer such that epsilon is greater than 1 over n, right? Even though you will say that if your epsilon is 1 over million, but if you choose your n to be trillion, then clearly 1 over n is greater than, so epsilon is greater than 1 over n, right? Then epsilon cannot be a member of one of this open set, right? And since this number fails to be the member of this one, therefore this epsilon cannot be in this infinite intersection, which is contradiction, right? Right? So this one must be an empty set. So, well, these intervals are closed, are going to play kind of very crucial role in proving the thing. All right. Okay. So I have very interesting applications of these nested interval theorems. AGM of two positive numbers. So before I introduce the AGM, so I will say that AGM stands for arithmetic and geometric mean of two numbers. Hey, hold on. So we know the definition of arithmetic mean, and we also know the geometric mean. But what do I mean by arithmetic and geometric mean of two numbers? Yeah, this is going to be, I guess, for most of you, this definition would be very new to you. And this arithmetic and geometric mean can only be defined by using the nested interval theorem. So it goes like this. Let us choose two positive numbers. Choose two positive numbers, which I will call A and G. And well, without losing too much generality, the greater guy will be A and the smaller guy will be G. Yeah. So suppose that I have chosen these two positive numbers. And from these two numbers, I want to build two sequences. And G1 is square root of A times G. So A1 is nothing but the arithmetic mean of these numbers, and G1 is the geometric mean of these two numbers. Okay, then between A and G, since these guys, A1 and G1s, they are the means of these two numbers, so there that means these two numbers must lie between these two numbers, right? But however, because of the AG inequality, so G1 must be less than or equals to A1, right? So we have these inequalities. Okay, and we can keep going on like this. AN plus 1 is AN plus GN over 2, and GN plus 1 is AN times GN, everything squared root. So we have the recursive relation. So therefore A2 is the arithmetic mean of these two numbers, and G2 is the geometric mean of these two numbers. And because of the construction, these numbers, they must follow these inequalities. And A2, A1, and A. And Gn is less than An for all n's. Okay, This reminds me of the nested intervals. So Gn and An is a nested intervals. Right? Yeah. So I was able to build a nested intervals. So because of the nested interval theorem, if you take the infinite intersections of these enclosed intervals, then this one is a non-empty set. Okay, good. So, well, a priori, so this infinite intersection may contain many different numbers, but I would like to show that there is precisely one element in this infinite intersection. By showing that this length of this interval is by showing that length of this nested intervals is tending to 0. All right. Let me begin from this. An plus 1 minus Gn plus 1. Yeah, since for all indices, A is greater than G, therefore this one must be positive, not negative. But An plus 1 is An plus Gn over 2 minus square root of An Gn. I want to rephrase this first term like this into An minus Gn, everything by 2 plus Gn minus this. Why? Why am I doing this? Because this is what? This is Gn, well, this is Gn plus 1. This is Gn plus 1, and comparing Gn and Gn plus 1, Gn plus 1 is slightly bigger than Gn, right? So therefore, this whole thing, these highlighted numbers should be always less than equals to 0, right? Okay, okay, good. So is less than this. So this guy is bounded by an minus Gn over 2. Okay, right? So an plus 1, Gn plus 1 is bounded by 1 over 2 times an minus Gn. And well, this factor of 1 over 2, it just carries over, but I want to apply the same argument towards an minus Gn. If we apply the same trick to this parenthesis, then I would get 1 over 2 carries over times another 1 over 2 times, but this time a index decreases by 1, right? And proceeding like this, probably I will end up with A1 minus G1. Okay. Okay, what is this? So this number tells us the length of the interval in plus 1, and which is clearly non-negative. But this number, this length of the interval, is bounded above by some constant multiple of exponential function. Therefore, as n goes to infinity, this number should be tending to 0. That means the length of this nested interval should be tending to 0 too. So an minus Gn is tending to 0. So now, because of the nested interval theorem, the sequence of nested intervals must have precisely one element in this infinite intersection, right? So we denote the only number in this infinite intersection, Gn by A, G, M of A and B, A and G. So this is the definition of arithmetic and geometric mean of these two numbers. Interesting, right? Yeah. Well, actually, so last night I was able to find some Wikipedia page, and that tells us the Professor Gauss, he was able to invent very interesting sequences that is tending to some constant multiple of pi. That is a very interesting. This is by using this AGM of two numbers. And he was able to prove that AGM of two numbers. I don't remember exactly. The first guy was 1, and the other was square root 2. I forgot. Sorry. The AGM of relatively two easy numbers turns out to be some constant multiple of pi. And that was very striking invention because, even before then, so the mathematicians, they had very interesting sequences that is converging to some constant multiple of pi's. Just like 1 minus 1 over third plus 1 over fifth minus 1 over seventh. Well, if you add up all these numbers, then that will then it was proved that these numbers, this series is tending to pi over 4, I guess. Yeah. But yeah, we had such a sequences, but the problem was the convergence of these sequences were extremely slow. But however, as you can see from in this argument, the convergence of this AGM of two numbers is as much fast as an exponential function. So Gauss was able to invent such a nice sequence, and that was converging really super fast. And that was very interesting, great invention of mathematicians. Yeah. Okay. All right. Okay. That is that. And we are turning to the next chapter, next section, about the Cauchy sequence. Mm. Okay. So in this definition, it is trying to define something called a Cauchy sequence. So what is that? Okay, all right. We say a sequence of numbers an, a Cauchy sequence, if for any epsilon, there is an integer n such that for indices n and m greater than n, an and am differs from each other by less than epsilon. Okay. Sounds very confusing. So I want to rephrase this by using the quantifiers. For any epsilon, there is a positive integer n satisfying the following property, such that if these two integers are greater than this number, then the an minus am is less than epsilon. This is the definition of A being Cauchy. This is the definition. Okay, all right. What do you think of this definition? Yeah, this definition looks somehow familiar to us. This one almost looks like the definition of converging sequence, right? Okay, right. Right. Actually, Cauchy sequence, the set of all Cauchy sequence is the same as set of all converging sequences. I mean, those converging sequences and Cauchy sequences, those two notions, they are both interchangeable. Because Cauchy sequence is automatically convergent sequence, and all convergent sequence must be Cauchy sequence. You can actually prove this. Well, but the question is, why do you even care about the Cauchy sequence? Because the Cauchy sequence is a converging sequence. The reason is very simple. Just try to remember the definition of the converging sequence. If you want to use the definition of the converging sequence, then you are supposed to have L over here, right? Not AM, but you're supposed to have L. So that, in other words, that means in order to make use of the definition of the converging sequence, then a priori, you should be able to pinpoint the exact location of L. That means if you do not know the exact location of the limit of your sequence, then you may not be able to say if that sequence is converging or divergent. Right? Okay. Well, I know some of you got also puzzled. So okay. So let me try imagine this hypothetical scenario. Suppose that you are given a random sequence. You do have no idea if the sequence is converging or diverging. Then, how can you check if the sequence is converging? How can you check if the sequence is converging? So Well, in order to check the sequence is convergent, then first of all, you will need to try to guess the exact location of L, right? For some cases, that is possible, but for most cases, that is almost impossible, right? So in that cases, the definition of the limit of sequence is almost useless. But however, so why the Cauchy sequence is a big deal? Because the definition of Cauchy sequence does not involve the location of L, right? It only tells us if you can check the difference between these two terms are less than epsilon, then you're good, right? So this is the reason that why we are interested in the Cauchy sequence. Okay, all right. So from now on, I'm going to prove two things. Every converging sequence must be a Cauchy sequence. So I will prove this one first. And on the other hand, also I want to prove that every Cauchy sequence must be convergent. I'm going to prove these two things. If I can prove both, if I can prove both statements, then that will prove that the set of all Cauchy sequences equals to the set of all converging sequences. Right? Yeah. Good. First, some example. Show that a sequence is a Cauchy sequence. Okay, all right. For any epsilon, I want to choose my n to be 1 over epsilon. Yeah. No, sorry. Yeah. And it must be always a integer. So yeah, I'll choose my n to be just any integer greater than 1 over epsilon. So in this case, then if two integers they are greater than n, then an minus am, which is just 1 over m minus 1 over m, by the triangle inequality, this is less than equals to 1 over m plus 1 over m, right? But since these two indices, they were greater than n, so these guys are less than 1 over n and less than 1 over n. And because of this, so these two things are also less than 2 times epsilon. Okay. Yeah, I know there are some of you doesn't like the existence of some constant multiple, but you know what I mean. So, well, being able to show that something is less than some constant multiple is actually the same as less than epsilon. So this proves the theorem. Okay, all right. Okay. So now I want to show that every converging sequence must be a Cauchy sequence. If a sequence is convergent, then it is a Cauchy sequence. Okay, so since A is a converging sequence, so we suppose that the sequence is converging to some number, which I will call A. Now, for any positive epsilon, now I want to divide the epsilon by 2, but this which is still a positive number. So for this epsilon, I can find the integer n such that if n is greater than n, then less than epsilon over 2. Okay, so if two integers are greater than this number, and then an minus am, which is, well, I am always free to add or subtract to same numbers. Well, but no different. And by using triangle inequality, so this is less than a minus am minus a, plus the another one is less than a minus am. But these two indices, n and m, they were known to be greater than these large m's. Therefore, this guy is less than epsilon over 2, and this guy is also less than epsilon over 2. So everything is less than epsilon. All right, so conclusion is, for any epsilon, I could find the integer n, and if those two indices are greater than this integer n, then the difference between these two terms are guaranteed to be less than epsilon. So this is Cauchy sequence. Okay, so this is good. Now, time to prove the other way around, the converse of the statement. Every Cauchy sequence must be convergent. Okay, this is quite a huge theorem. So this requires a couple of lemmas. 여러분, lemma가 뭔지 아세요 혹시? 보조 정리 맞아요. 예, 고마워요. 예. 큰 정리를 필요할 증명을 사용하기 위한 또 다른 조그만 정리를 보조 정리라고 하거든요. 근데 뭐 렘마라 그래서 대단한 거 아니고 그냥 또 다른 명제라고 생각하시면 돼요. And it goes like this. Every infinite sequence of numbers has an infinite monotone subsequence. Okay. So what is subsequence? Well, subsequence is just suppose that you have a sequence, just any sequence, and just choose any random numbers from the sequence, but without mixing the order, but preserving the order of terms. That is going to be the subsequence. So in mathematics, so in words, an is a sequence. Yeah, I am putting this additional n over here just to emphasize that this is a sequence for letter n. Suppose that this is my original sequence, then a subsequence A and K. I have two subscript. So here I am writing K just to emphasize that this is a sequence for not n but for K. Is such that K1 is less than K2, then NK1 is less than NK2. So this implication says that you cannot mix the order. The order must be preserved. So for instance, like this is your sequence. 1, 2, 3, 4, 5, 6, 7, 8, da da da. Then you can take any subsequence you like for instance, like 1, 3, well, maybe 6, 7. Okay, choose whatever you want. But only the order must be present. This is how you choose any random subsequence. Okay, now this is time to explain why this lemma must be true. This is the kind of interesting argument, but yeah, I can try to explain like this. Suppose that you are trying to find infinite, so monotone sequence means either increasing or decreasing sequence, right? So therefore, for any given infinite sequence, suppose that you want to choose a infinite increasing subsequence out of it. So, and if you can find such a nice increasing monotone sequence, then you're good. Then that means you are able to find infinite monotone subsequence from it. But suppose that is not possible. That means at some certain point, you cannot find any number that is greater than this number, right? At some certain point, you cannot find any number which is greater than this one. So, okay, so your attempt to find an infinite increasing sequence has been failed. Okay, what now? Then, after this point, you try to find another infinite increasing subsequence after that. If you can find another infinite increasing subsequence, then you're good. But suppose that your second attempt also failed. That means this guy. That means beyond this point, you are not able to find infinite. So you are not able to find any number that is greater than this guy, right? So then the third attempt, you try to find another infinite increasing subsequence after beyond this point. And if you are able to succeed at any of these attempts, then you are able to find infinite increasing monotone subsequence. But however, your infinite many attempt has been failed or all fail. Then that means the first number, the first upper bound, the second upper bound, and third upper bound, and fourth upper bound, they're going to be the decreasing sequences in the numbers, right? So in that case, you can find the infinite decreasing subsequence from the original sequence. Right? Yeah. Yeah, I'm just repeating the argument from our textbook. So if you're not pretty sure about that, then why don't you read it? 네, 되게 그럴싸하지 않아요? 그러니까 어떤 일정 시점 이후에 infinite increasing subsequence를 잡을 수가 없다면은 그럼 그 얘기인즉슨 요 포인트 이후에 있는 모든 텀들은 얘보다는 작다는 소리 아니야, 그치? 그치? 그래서 두 번째 시도에서 성공을 하면은 infinite subsequence 잡을 수 있는 거고 두 번째 시도에서도 실패한다면은 두 번째 시도에서도 요 일정 포인트 이상부터는 얘보다 더 큰 녀석이 없다는 소리잖아, 그치? 그치? 얘보다 높은 친구가 없다는 거잖아. 값이 높은 탕이 없다는 거지. 그러면은 첫 번째 어퍼 바운드, 두 번째 어퍼 바운드, 세 번째 어퍼 바운드, 이 어퍼 바운드들을 쭉 모아놓으면은 디크리징 시퀀스가 나오겠지. 그래요. Yeah, okay, that's that. Okay, now time to prove the theorem of 1.20. Okay, the first, we want to claim that every Cauchy sequence must be bounded. Why is that? Choose any epsilon. Yeah, in this case, for simplicity, I chose my epsilon to be 1. Then for this epsilon, I can find a integer, positive integer, and 0, such that if two indices are bigger than this integer, then an minus am is less than 1. Well, for this epsilon, yeah, I must be able to find such integer because we already know that our sequence is a Cauchy sequence. So an is a Cauchy sequence. Okay, all right. So in other words, an minus a. Now I will replace m by n0 plus 1. But even if I replace m by n0 plus 1, I still have this inequality. Why? Because n0 plus 1 is clearly greater than n0, right? So we have these inequalities. So in other words, a n0 plus 1 minus 1 and an and a n0 plus 1 and plus 1. Okay, so that means beyond this point, all the terms, they must be lying between this number, this constant, and that constant, right? So all the other terms beyond n0 must be, they are all bounded, right? So other than that, we only have the finitely many terms from a1 to an0, right? These are finitely many terms. Therefore, finding the upper bound of all these numbers is going to be the upper bound of this entire sequence, entire Cauchy sequence. So we know the sequence is bound. Okay. What's next? Suppose that an is a Cauchy sequence. Then there is a infinite monotone sequence. Monotone subsequence, which I will call A and K. Then by the monotone convergence theorem, this is an infinite monotone subsequence constructed from the original Cauchy sequence an. But because of A, we know the sequence an is bounded, right? Therefore, this subsequence is monotone sequence, which is also bounded. Therefore, this guy must be also convergent, right? So as k to the infinity, a and k is a. Lastly, well, this A was defined to be the limit of this infinite monotone sequence. But here, what I'm supposed to show is this limit of the original sequence is the same as the limit of this infinite monotone subsequence. For epsilon, there is n1 such that if k is greater than n1, a nk minus a is less than epsilon. The existence of such an n1 is given by this convergence. And since we know a is also Cauchy sequence, there is another number n2. Then is epsilon. Okay. Now we let n to be the max of n1 and n2. If n is greater than n, an minus a is less than an minus ank plus ank minus a. Well, you're free to add and subtract any number you want. But here, I require that this number to be nk to be greater than n. Then, by the triangle inequality, an minus ank and ank minus a. And well, this ank is greater than n, therefore an minus ank is less than epsilon. And also nk is greater than n, so therefore this guy minus this is also less than epsilon. So everything is less than 2 epsilon. So we're done. Okay. All right, great. Yeah. So therefore every Cauchy sequence is convergent. Yeah. All right, and this is the last section of the first chapter about the number E. So we want to talk about the Euler's constant. So since there are so many definitions, different definitions for the Euler's constant, but I guess the most widely known definition is the limit of this sequence. 1 plus 1 over n, everything raised to the nth power is converging to the limit of this sequence is defined to be the Euler's constant. Well, we know, we already know that. Compound interest, yeah. So so annual compounding and monthly compounding and daily compounding, weekly compounding. Well, as the compounding is getting more and more frequent, then you're right. Then your savings will gonna increase exponentially. So this is how I guess this is most of you are introduced to Euler's constant by using the definition. Anyway, how do you know that this sequence is convergent? If you just plug in just some random numbers, n equals 1, 2, and 3, 4, and it looks like the sequence is somehow increasing and converging to some number. But, well, being able to rely on intuition is not a greatest idea when you're trying to prove the sequence is convergent. So this time around, I will try to show you why this sequence must be convergent. 여러분 이거 혹시 수렴하는 거 증명해 보신 적 있어요? 그렇죠. 이거 상당히 생각보다 쉽지가 않아요. 한번 제가 증명, 그렇지만 오늘 이제 대학생이니까 한번 증명해 볼게요. We take, so to show that the sequence is convergent, we're going to use the arithmetic and geometric inequalities. From my viewpoint, this is one of the most clever applications of the age inequality. So let's take a look at this. I have these many numbers. This is n times. I have n the same numbers. So these are all the same numbers with one additional one. So combining all of them, we have total n plus 1 numbers, right? And I want to apply the age inequality for n plus numbers towards these numbers. Yeah, because they are all positive numbers, right? So age inequality for n plus 1 numbers. So what is the geometric mean of these numbers? Geometric mean, so we multiply everything and raise to 1 over n plus first power. So multiply everything. If we multiply everything, then it's going to be nth power. And since we are talking about the geometric mean, so raised by this much, right? So this is the geometric mean of these numbers. And on the other hand, what is the arithmetic mean of these numbers? Easy. You take a summation of all these numbers and divide it by n plus 1. So we have the same numbers plus 1. So this guy is going to be the arithmetic mean of these numbers. So combining this, I have n plus 1 and n plus 2, I guess. Yeah. This is 1 plus n plus 1, 1 over n plus 1. Okay. Okay. And this inequality is justified by age inequality. All right. Now, I want to raise the both sides of these inequalities by n plus first power. Then, n plus 1 over n is less than equals to 1 plus 1 over n plus 1, everything to n plus first power. Okay. All right. Okay. So if I say this guy to be my sequence En, so this is the sequence that was supposedly converging to the Euler constant. But this inequality tells us this sequence is actually an increasing sequence, right? This is an increasing sequence. Okay. So if we can show that this sequence is somehow bounded above, then I guess we are done. To show that, this time I want to consider this sequence. Well, this new sequence, which will be called f of n, but this is almost identical to En, but there is one difference. Well, this sequence has been raised to the nth power, but this guy has been raised to the n plus first power. Which one do you think is greater, comparing En and Fn? I am pretty sure that Fn is greater than En. Why? Because between these parentheses, I have a number that is slightly bigger than 1. And the two same numbers raised to the nth power, raised to the n plus first power. So yeah, I am pretty sure that this guy is greater than En. Okay, so En is less than Fn or n. All right, and now I want to show that the sequence is decreasing sequence. This time, I want to consider these numbers. Well, again, these are n plus 1 numbers. So we have the same numbers, but this time, not plus 1, but 1 minus n, and with 1 additional 1. I want to apply the age inequality for these numbers. And this is the geometric mean is 1 over n to the nth, everything to the 1 over n plus first power is less than equals to 1 over n plus 1 times n times 1 minus 1 over n plus 1. So this is the arithmetic and geometric inequality. Combining this is this n over n plus 1. Okay. So so n minus 1 over n to the so we have this. And I want to raise the both sides of this inequality by n plus first power. So everything to the nth is less than equals to n plus first. Okay. Okay. This doesn't. So it looks like it's leading us to nowhere. But yeah. Oh, right. Yeah. I want to take the reciprocal 역수 of everything. Then n over n minus 1, everything to the nth is now this inequality is now being reversed, and n plus 1 over n to the n plus first. And this final inequality is 1 minus 1 over n minus 1 plus, and to the n is greater than 1 over n to the n plus first power. Right. Yeah. Great. What is this? This is Fn. This is Fn. And this is what? This is Fn minus 1. Fn minus 1 is always greater than or equals to f of n. So Fn is decreasing. Okay, so what? So now we have two sequences, En and Fn. And these two sequences are satisfying these inequalities. So in total, so I can summarize like this. E1 is, these are a bunch of E1s, ENs. Then they are increasing. And F3, F2, and F1. So we have these two sequences. The one is increasing and the other one is decreasing, right? And if you take a close look of these inequalities, then I am also sure that by sequence, this guy is increasing, but bounded above. Say that this whole entire sequence En is bounded above by the first term of the F, right? Likewise, the sequence is decreasing, but the sequence is decreasing, but bounded below by E of, say, E of 1. So we have two sequences. One is bounded, increasing and bounded above, and the other one is decreasing, bounded below. And this also reminds me of the nested interval theorem. Nested. And next time, okay. So, all right. So, and that next time, yeah. So therefore, we know the sequence is increasing and bounded above. So we know that sequence must be convergent. And that the limit is defined to be the Euler's constant. Okay. Well, in fact, this is also converted to the same number. We can actually easily show that the difference between En minus An is converging to 0. And by the nested interval theorem, so therefore, this another sequence F is also converging down to the Euler's constant. Okay. I guess this is for today, and see you next time.